folks. My name is Greg Fleming, and I'm going to record today a kata that I'm doing in F#. It is the word search kata, which is reasonably well known and can be found on the internet fairly easily. In it, you are given an input sequence, which consists of the first line contains a list of words that should appear in the puzzle, and the rest of the input is multiple lines of characters separated by commas, in which you're supposed to find the words. The expected output should be in the form of a string, with each word followed by the location of the cells that make up that word. So here 06 is the I guess 0th column and the 6th row, so BONES, 06, 07, 08, etc. So I'm starting with a test already written that has the expected input and expected output. I'm treating this as an acceptance test. And the only other thing that I have a trivial implementation here which fails, which is just a method called solve that returns an empty string. And I have this utility function called dedent, which just takes input, nicely formatted input like this with new lines and leading spaces in it, and strips off the leading and trailing new lines and leading spaces on each line so that I can get the input formatted in the way that I expect it for the kata without having to make weird looking stuff in my tests. My tests can be formatted cleanly. Okay, so I'm going to go ahead and run the tests themselves, and I have here a useful command for that. And .NET Watch will continuously run the tests whenever a file is saved, so I shouldn't have to manually run them each time this goes through. Wait a minute, it's already skipped. Aha! I didn't mean to start with it skipped. I meant to start there. Alright, I meant to start with a failing test. I am going to skip it here immediately after, so that was an oops. Alright, so what I've got is a failure here. I expected this string, and I got an empty string, which is to be expected because our implementation consists of just returning an empty string. So now I'm actually going to skip that test, leaving myself with no running tests, and start working on the implementation. What I'm going to do first is work on parsing the puzzle, and the input for the parse function will only be the lines containing characters. I'm not going to input this line to the parsing section, and I'll work out how to do that later. So I'm going to have a function called parse, and what it should do is produce a list of cells given the input. Actually, it's producing a sequence of cells. The difference between sequence and list in F# is a little bit like the difference between enumerable and list in other .NET languages. A sequence is sort of more primitive. It's more abstract. Less is known about it than a list. Most of the stuff we'll do in this implementation has to do with sequences instead of lists, which is why I'm making a point of it. Okay, so first I'm going to start with a puzzle. And I'm going to do a simple puzzle. Use dedent to get rid of the leading and trailing spaces. One more quote. These three quotation mark things are sort of here docs syntax in F#. They'll let you make multi-line string literals that are pre-formatted. And just A, B, C, D. And then I'm going to define what my expected output is. And this is a list. The square brackets are lists in F#. And each member of the list is a record with a letter, which is single quotes, the character at that position, and the X coordinate and the Y coordinate. Make a few more of those. Got to get my formatting right, or I'll be obsessing over that later. F0. Okay. These red squigglies are from the Ionide plugin. I'm using many plugins here, but the important one is this Ionide F#, which is providing F# language support and helping me with things like the type signatures of methods and sort of linting as I go. There are some downsides to it too, but we'll probably come across those in the course of this implementation. But the red squigglies are because it does not want you to end the function with a let. Let can't be the last thing. And it's not going to be. We're going to do something else here. And okay, so we're going to parse the input, then we're going to assert that the result is equal to this list of expected cells. And the compiler is very mad about this for a number of reasons. This is one of the downsides of Ionide. Sometimes it gets confused and does not actually do what it's supposed to when you save a file. Okay, so the main thing the compiler is mad about is it can't infer the type of this record based on its contents because I don't have a user-defined type with a field called letter in it. Let's go make one. And this type has a letter, which is a character, and an x-coordinate, which is an int, and a y-coordinate, which is also an int. Let's fix this formatting. Here the linter is mad because I'm not using Pascal case for my records. I'm not going to do that. I'm just going to ignore that linter for now. Are you still not compiling? This expression was expected to have type char, but here has quote A times B. A semicolon is used to separate. Aha! It's mad about this comma, which should in fact be a semicolon. It is quite right. Okay, now it's mad because there's nothing called parse. And I'm going to declare a function called parse. And I'm just going to return, not an empty string, I'm going to return an empty sequence right now. And the reason that I'm doing that is I want to declare the type signature of this method, which is it takes a type of a thing, and it takes a thing of unknown type, and returns a sequence of some other unknown type. And then I wanted to see a failing assertion, which is accurate. So this assertion is now failing. The red squiggly is out of date. You can ignore it for now. The assertion is correctly failing because it's saying it wants to see this list of expected cells, and it's actually seeing an empty sequence. I like to see a failing test before I move on to actually doing the implementation. A test that's failing not because of syntax or compiler errors, but because the logic is not actually implemented yet. And that's what I've gotten to here, and that's the main reason that I had this function return an empty sequence before actually going on to implement it, which I will do now. We're going to do this with a pipeline. So we're going to take input and pass it and pipe it through this following sequence of functions. Pipelines seem to be very idiomatic in F#. A lot of documentation and code seems to use them. So I'm going to use them pretty heavily in this implementation. First, we're going to split the input by line. Just by the new line character. And I don't have a function called split yet, so I'm going to see some squigglies. And then once I've done that, I'm going to map it. I'm going to map it with its index present. So here, the map_i function requires a function with two parameters, an int and another thing, and it returns something else. So the function I'm going to pass here is called Parseline, and that also doesn't exist yet. So what I'm going to do is I'm going to parse each line independently, and each line will give me a sequence of cells. And then I'm going to take those multiple sequences of cells and join them together into one long sequence with just sequence.concat. Okay, so that's my intent. This is what Ron Jeffries calls programming my intention, where I outline sort of from the top down the general structure of what I have in mind for the implementation and then fill in the details as I go. So I'm going to make a function called split, and this is going to take a delimiter and a string. We'll just call it input, and it's going to return input.split delimiter. Okay, so this is mad. The split function that I'm looking for here is actually the .NET Standard Library string function, but F# does not know that this is a string. I have to tell it that this is a string. Usually F#'s type inference is pretty good, but not in this case. And finally, also, here, split has multiple overrides. And the F# compiler guessed that I wanted the one with a character array. I didn't. I wanted the one with just a string. So I'm going to use a type specification again to clear that up. Okay, so now it's fine with the split function. And you can see that this ionide plugin here is the type annotations that it's providing in my editor are really helpful in terms of figuring out this kind of type inference tangles in F#. Without ionide, I get really confused. Okay, so we also have to make a thing called Parseline. And this takes an integer, which is the index of which line we're on. And that's the map_i function provides that. I'm going to call that index y, because that describes, which sort of y coordinate we're at. And then the line itself is a second parameter. And what I'm going to do here is, again, do a pipeline where I take the line and first I split it by character. I split it by comma. So I get a sequence of the characters themselves without the commas. And what I want to do with that sequence that I get is, again, I want to map_i it. And here we're going to define a lambda function, which takes the index of the line of the member of the sequence that we're passing. So I'm going to call that x in this case because we're talking about which character in the line it is that we're dealing with in this lambda. And then the second thing is just the character itself. And what I do with those arguments is I just make a new record. I can't just use C directly because C in this case is a string. I have to get the character out of it. So I'm just going to extract the first character. And then x is the x coordinate, y is the y coordinate. Alright, all my squigglies are gone. I'm going to attempt to run this, and I think, if I haven't made a mistake, this test should pass. Great. So now we have a test that's saying when we parse the input, it comes out into a list of cells with the coordinates of each cell. And we're going to use those list of cells to do various things. It's going to be the basis of the rest of our solution for this kata. So next I'm going to do a couple of utility functions that take lists of cells, or sequences of cells I should say, and extract useful facts about them. In particular, I want to be able to get the word out, and I want to be able to get this sequence of positions out of it. I'm going to make a function called toWord. Let's describe it. Like so. And I'm going to give a sample sequence of cells just to be the data for this particular couple of functions. And I'm just going to take some of this, And let's make it more of a diagonal. So 0, 0, 1, 1, and 2, 2. Just so that it's sort of closer to a typical solution like we might see in the puzzle. Then I'm going to assert that two words should just pull the letters out in order and concatenate them. So like so. And again, why are you mad here? Ah, there's no equal sign. Okay. And it's justifiably angry here because I have no function called toWord yet. I'm going to make one here in a second. I'm leaving this solve at the bottom because this is our sort of outermost function call. And in F#, when you call functions declared in the same file, the callee has to be declared higher up in the file. I was kind of angry when I learned this about F#. It's like, why can't we organize things how we want in the file? It seems weird. But that's the way it is, so we got to do it. Okay, so I was making a thing called toWord. And this takes a sequence of cells, whoops, and it returns the letters. So I'm going to take each cell, cells, I'm going to map it through sequence.map, and I'm going to pass a lambda, and for the cell we're going to say cell.letter, and then we're going to take the output of that, which should, see right now this is a sequence of characters. I don't want that, I want to join the sequence together. As a string. No. This is an interesting point. This string, when I just reference string like this, is the F# library string. And it does not understand about a thing called characters. It just wants to work with other strings. But if I use the standard .NET library version that's not part of the F# library specifically, I can get away with concatenating characters. So I do that by just, there's a couple ways to do it, but I'm going to just refer to it directly as, and that wants to be capital C concat, because that is how the standard .NET library spells things. All right. So my test passes. Next I'm going to make another function called toPath. And path is just a nomenclature that I've thought up myself for this kind of list of locations of cells. It's sort of the path that the word takes through the puzzle. I don't expect anybody else to necessarily use that notation, but I'm going to in the course of this implementation. Possibly longer than it's strictly necessary, but we're going to live with it. And for this sample sequence, the first character should be at 0, 0, and the second is 1, 1, and the third is 2, 2. And this is just toPath sample sequence. Again, I don't have a thing called toPath yet, so the compiler's going to be mad. Right. You know what, I forgot to, when I was making toWord, I forgot to see a failing test first. So let's not make that mistake here. Let's just return an empty string so that I can see the test fail. It's useful to see the test failing because a common mistake that people make in test-driven development is that they write a test which doesn't actually do what they think it does. It doesn't constrain the solution in the way they expect, and if they don't ever see it fail, then they won't know. They won't know that the test they've written is incorrect. I've made this mistake many times, and hopefully I sometimes learn from my mistakes, and I would like to, I'm trying to practice the discipline of seeing my tests fail before I implement the solution. Okay, so now I have an expected failure message. I expected this string and I got an empty string. Perfect. So I'm going to take the cells and again pipe them through map. But what I passed to map here, I'm going to write a function called toLocation. And again, I'm going to concatenate them. Here, I expect to get actual strings out of toLocation, so I can just use the F# library concat, which specifies a character that you can use to join them together with, which we'll do a comma in this case. And now we just have to do toLocation. So given a cell, its location is a sort of a XY coordinate pair like this, where the first letter is cell.x and the second one is cell.y. Good. So I'm hoping to see this test pass now, assuming I've made no mistakes. Great. Okay. Sometimes when I do this kata, I do a third utility function here called toAnswer, which sort of puts the word and the path together with a colon between them so that it's in the format of this answer. But I think I'm not going to do that this time. What I've been doing instead is implementing that function in line as part of this final solve. And I think I like that. So we'll move on now to actually finding words in the puzzle. About time, huh? So I want a function called find, and what it should do first is I want to make sure that it returns sequences of characters so that I can use my utility functions on them. And to test this, I'm just going to do a really trivial puzzle. Yeah. I'm going to parse some input, and the input I'm going to use is just ABC, all on one line, nothing fancy. And I'm going to assert, I'm going to do this thing with the expected cells again, because I want to explicitly specify the entire sequence of cells here. And that is actually correct. So here I want to find the word AB in this puzzle. So I'm going to pass puzzle as the first argument and the word AB as the second argument. And I'm going to assert that the outcome is this list of cells. And this, I expect this to fail because I got squiggles on the whole thing because there's nothing called find, and therefore it can't figure out what type of expression this assert equal is. But the main problem is there's no method called find. Find takes a list of cells, a word, and returns a sequence. Okay, so now we have a good failing assertion. I expected this sequence here, and I got an empty sequence. Now I can actually start working on my implementation. So the way I'm going to do this is I'm going to pick out a starting cell, and that's just going to be the very first cell in the puzzle. And then I'm going to say I need a next cell from that. And I'm going to find the cell in the puzzle that is next to my starting cell. So I'm going to find one with a lambda. And I want the one that's one to the right of my starting cell. And then I'm just going to return a literal sequence of start followed by next. Next cell. Okay. I think that this will pass this test. This is obviously a terrible implementation, but it is the simplest thing that could work given the tests that I have, and this will force me to write more tests to constrain the solution to something more useful. So the first thing that we're going to do is I'd like to be able to find words that are not starting at the very first character in the puzzle. So I want to be able to find them anywhere within the first line. And let's make a puzzle that demonstrates this. Let's do ABC again, but this time we'll search for BC. And what I'm going to do here is, because all of the letters in my puzzle are unique and only occur in one place, I can make assertions about the sequence that is returned simply by asserting on the letters of the cells. Because if I have a sequence that returns the letter B, that B only came from one place. I don't need to assert about its location because the location can't be anywhere other than this second character in the first line. When I have puzzles where the letters repeat in my tests, I have to be more explicit about the locations. So I'm going to try most of the time to make my puzzles not repeat letters unless it's necessary for the test. So what does that mean? That means that I can, in this assertion, I can just say AB, and I can find this BC actually, and I'm going to pipe that sequence of cells through to Word. I have squigglies because I forgot to parse my puzzle. It's just a string now, not a sequence of cells. Okay. What I expect this to do is fail and say that it found AB, because we're not actually looking for a letter that matches the word we're passing in. We're just taking the first character and the one that's next to it. So now I need to, instead of just using the very first character, I need to find one that matches the first character of the word. So let's pull that first character out. And we're going to find, with the lambda, we're going to find a cell that matches this predicate defined by the lambda. And the predicate is that the cell's letter is equal to the first character. Okay. So I expect this to pass. Our algorithm found the first character matching the start of the word, this one, and then just returned that character and whatever the heck was to the right of it. So obviously this is still not a great implementation. There are many things wrong with it. It doesn't find words anywhere except the first line. It only finds words that are 2 letters long. And it doesn't actually care if the word matches what you asked for. It only matches on the starting character. We're going to fix all those problems, but the first one I'm going to look at is the length of the word. To do that, I'm going to make a longer puzzle. And let's just search for BCDE. So this probably will fail saying it only found the word BC. Uh-oh, unexpected pipe. Yes, that's supposed to be pipe through greater than to actually make a pipeline in F#. Okay, and that's what I expected. Okay, so to do this, I need to transform this next cell business. I need to not just take the cell that's immediately to the right of it and only that cell. I need to build a generator that can give me as many cells as I need based on an implementation. And what I'm going to do that is I'm going to transform this next cell from a variable into a function by passing an argument to it. And then I'm going to, instead of the nth cell in my sequence is going to be the one that is n characters to the right of the starting cell. And then I'm going to take a sequence of those, let's see, I'm going to initialize an infinite sequence. And this is how you do generators in F#. You give the sequence init infinite a generator function, which is this next cell. Then I don't want actually an infinite answer. I only want the number of characters that are in the word I asked for. So I'm going to take some of this sequence, and the length I'm going to take is the length of the word. And then I'm just going to end up returning this candidate. Okay, good. So now we've gone from done that step of the implementation where we have to go from taking one cell more than was asked for in the word to taking as many more cells as were asked for in the word. And that transition from doing once to doing it sequentially, I feel like is an important step in many implementations. Okay, so now that we can find words of any length, let's work on the next things. I think next I'm going to handle the fact that we are not actually matching the full word, we're only matching the first character. And a test that demonstrates the problem with that looks something like this. Let's just do A, B. So I'm going to search for AB, and our current implementation is going to give me these first two characters, and what I want it to do is give me those two characters. So here's a situation, because I have multiple A's, where I have to be explicit about the location that I'm, of the cells I'm looking at. So I'm actually going to transform the outcome to a location, to a path, excuse me, and assert on the full path. So the expected will here be 0, 1, 2, 3, 3, 0, and 4, 0. Find puzzle AB and pipe through to path. Oh, I forgot to parse it again. Okay. As I expected, the actual cells produced were 0, 0, and 1, 0. So what I'm going to do now is I'm going to look at each starting sequence. So I'm not just going to look at the very first character that matches my letter. I'm going to find all of them. So I'm going to from find to filter, and that's going to return more than one. So I'm going to call this starts. That means that I need to get this start from somewhere. I'm going to have to loop over the possible starts and pass this in as a parameter. So I'm going to pass start here. And the reason that I'm trying to put start as the first parameter instead of the second parameter is so that I can do partial function evaluation here and put start as a parameter on this. So instead of so again, this is going from a variable to a function that takes a parameter called start. And I'm going to put start there, and I have to specify that start is a parameter for next cell, not for sequence.initInfinite. Okay, so this return value no longer makes sense. I don't want to return a function. You can see up here that Ionide is confused about the type that I'm returning, or Ionide is quite correct about the type, but I'm not returning the right type. So what I need to do is loop over all the starts and call this candidate function on them, map over the starts. Stop. And then I only want to return the one that matches the word we're looking for. I don't have a function called matches yet, but we can go ahead and make one. A candidate here is going to be, well, right now candidate refers to this word, to this function. But what I want to be the case is that candidate refers to a sequence of cells that may be the solution that we're looking for. The solution meaning the location of the word in the puzzle. So the candidate matches the word if the word itself is equal to the candidate when converted to a word. Come on, there we go. So I think I've gotten my return type back to a sequence of cells, which is what I expect. So I think that this ought to potentially pass, assuming that I've done this right. And it does. Great. I want to rename this to something more useful. Let's see, can I rename with that? Yeah. Okay, so now it's a function it's more clear about what I'm actually doing here. It's a function that takes a starting cell and builds a candidate at that cell. And the only way that we know how to build a candidate right now is just by going straight to the right. Okay, what's our next test? I think it's time to start looking at other lines other than the first line of the puzzle. So we're going to make a puzzle with more than one line. Just put a new line right there in it. And let's just search for CD. And I expect this to fail right now because it's going to find the C character and then try to find a sequence from there that matches CD, and it's not going to find one. So it's going to throw an exception saying key not found, and that's from this find right here. This kata does not call for doing error handling to handle the scenario that the word is not found in the puzzle. We're just making the assumption that the word is always found. So I'm not going to handle a missing word, a word that we can't find. Instead, I'm just going to fix the implementation so that we can find the word we're looking for. And the way that we do it is we need to look at this next cell generator. It needs to look at cells that are not only have the same x-coordinate as whose x-coordinate is not just one more than the starting cell, but also whose y-coordinate is on the same line as the starting cell. So I just need an and here. And cell.y is equal to start.y. I think that this will pass. Okay. So given that we can do all of these things now, I think it's finally time to start looking at moving in different directions from our starting word. And this is another one of the transformative parts of this kata. And taking this step can be a little bit difficult. First, I'm going to write the test, and I'm going to write not a fact this time, but a theory, which is a parameterized test in XUnit. And I want to inline data, and I just want to pass the word that I'm finding. And I'm going to start with something called C1. I'll explain what that is in a moment. And because I'm parameterizing this function is the test function takes a parameter, which is the word that I'm looking for. And I'm going to build a specific puzzle so that this word makes sense. The character C is going to be in the middle, and the numbers 1, 2, 3, 4, 5, 6, 7, 8 are going to be around the outside, representing all the possible directions that C can go. So the input, the puzzle is just going to be, we're going to parse that string, and we're going to have to do dedent. And it just looks like 1, 2, 3, 4, C for center, 5, and then 6, 7, 8 on the final line. So the actual assertion here is that the word parameter matches what we get when we search for that word. I expect this to fail because obviously our solution does not know how to go northwest from the found character. It only knows how to go east. Oh, come on, Ionide. And what I'm going to do at this point is I'm not actually going to implement this right away. I'm going to put in the other test parameterization, which does map what we can do, and comment that out for the moment. I expect this to pass because we know how to go east from our central character. So what I'm going to try to do now is a thing that I heard, a process that I heard attributed to Kent Beck. I heard this from Sandy Metz in one of her talks. I think it was the one about the Gilded Rose kata. And Sandy Metz says that Kent Beck says this: first, make the change easy, then make the easy change. Asterisk, step 1 may be hard. So that's what I'm going to try to do. I'm going to try to do some refactoring while preserving these passing tests in such a way that it makes it easy to add the concept of direction to this search algorithm. And where I'm going to start is here, because this already has a direction built into it. It's just that the direction is only east. And we sort of have that assumption baked into our code. So I'm going to pull it out and make it explicit and then do some other things. So first I want to introduce the concept of a direction as a type. And direction is going to be almost identical to cell except with no letter. So now I'm going to have to do some work because all of this type inference that the F# compiler has been doing is going to get confused by the fact that I have two types now with similar looking names. So I'm going to have to do some explicit type specification. And I've sort of learned through practice that there's two places that I need to do this. One of them is here. And I believe the other one is in this next cell. I think if I do that, all the rest of them should follow along by type inference. Okay, so we're back to passing. Next, I want to introduce an explicit concept of east. And that's just x changes by 1 and y changes by 0. Y. Test should still pass. Okay. And now I want to, instead of just putting n here, I want to say n times east dot x and n times east dot y. East dot y is 0, so this clause evaluates to 0, and our test should still pass. Okay, so next I want to take this explicit hard-coded east, and I want to introduce it as a parameter so that it can be passed in from outside instead. So I'm going to put that here, I think. The order of the parameters is a little bit important because I want to do partial function evaluation later, and I think that this is right, but I might get it wrong, and we'll see. So I'm going to make a thing called direction, and east is the direction, and then I need to pass east in from the outside. And I hope you can see where this is going a little bit, that the concept of direction is becoming more abstract and controlled from the outside. And eventually I'm going to have a list of directions, and I'm going to loop over each direction as well as over each start. And that will give me my algorithm for finding potential candidate solutions. Okay, so now we're passing in east here, and I'm going to move it one step farther out. And whoop. Okay. So here's where I got this wrong. In order to do partial function evaluation here, I need this to be first. But this actually may need to change in a minute. Okay. So again, I don't want to just do east. I want a list of directions, which right now is only east. But then I want to loop over that list to make my solutions. So let's see. For each start, I want to find the candidates at that starting location. And the way we do that is we're going to loop over directions. Okay, yeah, so here's where I need to put the order of the parameters back where it was. And parens around that so it knows how to apply. And then I'm going to take this and put it down on new lines so I get some help from the type inference. Okay. So here's a problem. Right now I have this sequence.map find candidates app nests the types too much. So building a candidate produces a sequence of cells. A sequence of cells is a candidate solution. It is sort of congruent to a word. But a sequence of cells is more than one candidate solution. That's fine. We can loop through a list and figure out which of them matches. But a sequence of sequences of cells, that's too many. That's a multi-dimensional list of candidate solutions, and that's going to be too bad. We need to flatten that out. And the way that we're going to do that is instead of map here, I'm going to use a function called collect, which is like a flat map in other languages. And so that takes one level off. Instead of having a multi-dimensional array, it's just going to flatten the return values. And in theory, I should have my types all lined up, and I should get back to passing here. Okay. So what I'm doing at this point is I'm taking every starting cell that matches the first character of the word, and I'm producing a list of candidates from each starting cell, I'm going in every direction in my list, which right now is only east, and making an infinite sequence of cells starting at that location and going in that direction, and taking the length of the word from that infinite sequence of cells. And that's how I produce all of the candidates that could possibly be the answer from this starting location. I do that for all the starting cells, and then I find the first thing in that whole jumble that matches the word I've been asked to find. So that's my algorithm, and I think it's pretty reasonable. I could probably do somewhat better with the naming, but I'm kind of drawing a blank right now on what names would be better for here. So I'm going to leave it alone and move on and maybe come back to that in a minute. But I think it's time to restore this test because I think we can make it pass pretty easily now. First I want to see it fail again, just to make sure I haven't accidentally done something I didn't expect to. Yeah, it does fail. Now I'm going to put a new direction in my list. I don't need the word east anymore. East is no different from any other direction. I'm going to do northwest is going to be -1, -1. And I do have to have a space here or F# gets confused. So I'm going to space these all out. And I'll fix the formatting here in a second. But I think that this should be enough to make this test pass. Now I know how to look in... Whoa, that's no good. Ah, yes, I've remembered something. Okay. So the reason this didn't pass is not the test we're actually looking at. It's a different test failed. Locate words on any line failed. And locate words from any matching starting character failed, and probably some other ones. And what's happened here is now that I know how to look in different directions, it's failing on these tests because it like starts, say, at this character and says, all right, I want to look northwest. But there is no northwest from here. It falls off the edge of the puzzle and runs into a situation where it doesn't know how to generate the sequence because there is no matching character whose y-coordinate is one less than this character's y-coordinate. And that's because we're using sequence.find here. Sequence.find expects to throw an exception if it can't find a matching cell. But we have situations where we know we're not going to be able to find a matching cell, so we have to use something else. We're going to change this to try-find. And try-find returns one of these option types in F#, which is either the answer that we're looking for or null. And the type has changed. So now I'm not doing sequences of cells. I'm doing sequences of cell options. That's no good. We want to get back to sequences of cells. And the way that we do that is when we have a sequence popped out of sequence.take, we're going to take only the members of that sequence that are real things and not options. And I don't know exactly what this does, but I've learned that this is the way to do this. We call sequence.choose on the sequence, and what we pass it is a function called ID. And I believe that this is kind of like a filter, where basically we're saying, like, filter out the ones whose ID value is truthy, and I think that null comes out as sort of falsy. That's probably not exactly accurate, but that's the way I'm thinking about it right now. I really ought to go look up what this choose does for real, and I will at some point. But for now, we've converted our sequence back to from sequence cell options into a sequence of cells. And that's closer to what we actually want, and now our tests are passing. So I want to format this better, and I'll show you why in a second here. But I want to use this format for all of my directions. So the second line now is east. It's just formatted in the same way as the first one. And I do have to have this, or something like this format for the first one, because if I put the minus sign right next to the equals, Charts gets confused. Okay. So I'm going to introduce more directions now. And I can do this easily in my parameterized test just by saying C2, C3, 4, 6, 7, 8. These should all fail. Or that is to say, 6 of them should fail. Yep, 6 failed tests. But we know what they all are, and we can just go ahead and introduce the rest of the directions. On the first line of the puzzle, represented by the y-coordinate -1, we're just going to do x is -1, or x is 0, or x is +1. On the middle line of the puzzle, there's no x is 0 and y is 0. That would mean go no direction and only take the specific cell we found. But we could go x -1 or x +1. And then the rest is just going to all be with the y-coordinate increasing by 1. Whoops. Okay. I am using the IdeaVim plugin, not IdeaVim, but Vim emulation from VS Code. And every once in a while, my fingers don't do what I want them to. Usually it saves me time. Okay. And I separated these only so that I could think about them together. But really this is just all the directions that we want to go. And it so happens that this list of directions is in the same order as this list of assertions. That really doesn't matter. It's not important. Okay, so our find is basically done at this point. We can find words going in any direction, words of any length, words that start anywhere in the puzzle and on any line or any position within that line. And that's not impeded by the presence of other starting characters that could be within those lines that don't produce the right solution. So I think we can find the words that we need to. We just need to put it all together and actually implement our solve function. So it's time to go back all the way to the top to our acceptance test and take out this skip. Make sure it's still failing. I don't know how it wouldn't be failing, but I feel better if I make sure my test is doing what I expect them to. Good, yeah. So I'm going to sort of solve this one step at a time by, rather than making the test pass, I'm going to make the test's error message change in a way that gives me confidence I'm moving forward and I'm on the right track. So first I'm going to start by pulling out the lines of the puzzle. And that's just, I take the input and I call split on it with new line. Whoops. Come on fingers. There we go. And I'm going to return the first line. And that's going to give me a quick sort of sanity check as to whether I'm doing what I think I'm doing with this input string. And I expect to see something like Bones, Con, Kirk, Scotty, etc. And I do. So that gives me some confidence that that I know how to pull the words that I'm looking for out of this input section. Next, I'm going to try to transform this into the list of words itself. And I'm going to take that first line, and I'm going to split it by comma. And I'm going to return, let's just do the first one. So I expect this to only return me the word bones. Okay, good. So now I'm going to take, I'm going to try to find the word bones in the puzzle and produce its solution. So here's where I'm going to implement that toAnswer function. No, sorry, I'm getting ahead of myself. I'm not going to do toAnswer yet. First I need the puzzle itself. I need to take the rest of the lines, so instead of sequence.head, I'm going to do sequence.tail, which is everything except the head. And I'm going to put those back together so that I can call parse on them. And then finally, I'm going to call parse on them. And the result of this pipeline, I'm going to stick into a variable called puzzle. Finally, now is when I need my toAnswer function. And I'm going to sprintf again. And this is going to say, I want the word here and a colon and another string, which is its path. And sorry, I need to find it first. Find puzzle word pipe through to path. And finally, I'm going to return the answer for this first word. So I expect to get this first line, bones 6, 7, 8, 9, 10. And then it should fail at the second word because I don't have con yet. Okay, so I've gotten the answer right for the first word. Let's just do it for the rest of them. I'm going to pipe through sequence.map to answer. That should get me a sequence of the answers to each word. And finally, I'm going to just concatenate them together with new lines. String concatenate. Not bells. And I think there's a reasonable chance this will actually pass. Excellent, it did. Okay, so we're passing our acceptance test. We've actually managed to parse this entire sequence of stuff. We found the words. We found each word within the puzzle. So here's bones down the left side. And we formatted the output in the expected format. I would like to be able to come back to this area at this point and look at the names of these things again and see if we can maybe clean this up some, do some refactoring. Now that we're fully finished with our solution and all of our tests are passing, can we clean this up at all? Can I leave future me, who has to do maintenance and add features on this, with an easier task of understanding it after my tiny brain has forgotten everything I knew? So find candidates at is a name that I'm not super happy with. What if I put those up there? It's not too bad. Let's call it find all candidates starting at, something like that. Starting here. That might be better. I think I might be happy with that. Yeah. I think that particularly in this kind of sort of dense functional code, the names of functions matters a lot. And that being able to clearly express what each function does when you're doing this kind of piping and collecting and building up multi-level data structures from complicated functional programming expressions if you can clearly understand what each function does, then that goes a long ways towards making it possible to understand what the sequence of expression does. Probably there are better names that could be done, but this is what I'm coming up with right now. So I think this is where I'm going to leave things. Just make sure my test actually passed, since I've done some refactoring. And assuming that the tests actually pass, I'm going to finish my recording here and say thanks for watching. If you made it all the way through this long Kata video, I really appreciate your time. Thanks. Take care. Bye.